Okay, cool. Yeah. So, hello everyone. My name is Dennis. I'm part of IP Shipyard and specifically at the ProLab team. So, IP Shipyard is the umbrella organization that partially maintains libp2p, but also IPFS, and has a lot of contributors, core contributors there. And I'm here to talk to you about ProLab's core mission here. So, we built a few, or quite a few, tools for monitoring the health of libp2p-based peer-to-peer networks. And if I wanted to summarize our mission in one sentence, it would be: we carry out rigorous P2P protocol measurements and benchmarking in order to make P2P networks faster, safer, and more resilient. And you might ask, why would you want to do it? And I think the picture on the right summarizes it really well. Things might work, but maybe not as you expect them to work. And if you put pressure on the system, it might fall apart. So this is that. Nearly everything that happens on a blockchain relies, or at least should rely, on a P2P system, yet this is a very explored area. Yesterday I've been to the DuneCon conference, and what I learned, this is a huge ecosystem and community, but the analytics that we carry out there are exclusively on on-chain data, like transactions analysis and so on, but these transactions need to be transmitted over the network, and this is where we come in. So this is one layer below and doesn't get as much attention at all. People just assume that it works, and this is where we come in and try to measure things and see that it works. So, and this is also the obligatory XKCD picture here. Cool, so this is an overview of the tools that we have built. I will specifically focus on these tools in this talk, give an introduction of what they do. So this and go to this list again, and I will say a few words to all of them. So network topology is one of our core things that we measure, and we have as the first tool Nebula here, which is as a network agnostic DHT crawler. It supports a variety of networks, mostly libp based. And how it works is, so Nebula has a hard-coded set of bootstrap peers, and it asks those peers, hey, do you know any more peers of the network? Then the bootstrap peers respond with a list of peers that it knows. Nebula puts it in a queue, and then it takes the next peer of that queue and continues the process until we don't have any peers in the network left. And by these measures, we are able to get a comprehensive view of all peers that are discoverable in a network. And we use this to build a topology map of which peers are actually participating there and how many servers are there in the network and so on and so forth. Then also, after we have identified these peers, we can also do liveliness monitoring. So how long do they stay online, and when do they churn? What's the just the dynamicity of the network. And on the right-hand side, you can see mostly libp2p-based networks, but also the Ethereum consensus and execution layer is there, which uses a different DHT implementation, namely DiskV4 and DiskV5. And I won't say more on this tool yet, because there's a talk from last year, which I would recommend if you want to learn more. But this tool is a basis for a few of the other tools. One of the latest additions to our toolset is ANTS, which is the other side of the equation. So Nebula measures the DHT peers, server peers, so everyone that's publicly reachable on the network. And ANTS, which is built by my dear colleague Guy, measures the DHT clients in a network. So it does this by covering the DHT key space very comprehensively and deploying DHT servers in certain locations in this key space, and then monitoring all the incoming requests that are from that are made from DHT clients. And we measure, or we track these requests, and at the end we can tell within 24 hours we saw X number of clients interacting with the network. And there's also an automatic adjustment to network size, which is relevant for some networks that have, for example, daily periodicity. And to get into a bit more detail with the methodology, so if you think of this line here as the DHT key space, and you have certain regular DHT server peers of the network randomly distributed in that key space, then we take our ANTs and deploy them in distributed distances, like very carefully chosen spots in this key space. so that when a DHT client joins the network, so it doesn't really join the network, but the crucial thing that the DHT client would do is build up its own routing table. And one of the first thing that it does is it looks for all the peers, the 20 closest peers usually, that are the closest to itself. And if we deploy these regular distances at in such a way that this request to the closest peers for itself would always end up in one of these ends, we are able to always identify like every DHT client that will join the network. So this client will look for its closest peers in this key space, and one of these requests, as you can see, will end up on this green line here, and this request would be tracked in our database, and this is how we could identify clients that are interacting with the network. So we have both sides here, so the DHT servers and DHT clients that we can measure here. And so I have a quiz for you. This allows us to measure the topology and also get information about, for example, data centers. Like, are these servers running on data centers? And so what do you think? Which Ethereum implementation is least dependent on centralized cloud infrastructure? What, sorry? So it would be Nimbus, Prism, Lighthouse, Lodestar. Lodestar? Geth? Oh, I mean consensus clients. Prism, okay. Okay, I have Prism. What did you say, sorry? Nimbus, okay. Actually, that's right. So it's Nimbus. But it's also, you need to look deeper, of course, because Nimbus is one of the least deployed client implementations. So here you can see all the different implementations that we track. On the x-axis, you have the time, and on the y-axis, the servers that are running on cloud infrastructure or non-cloud infrastructure. And if you look at the ratio, Nimbus is actually best, but Nimbus has only around 300 peers in the network. And then on the top left and in the center on the top, you have Prism and Lighthouse. You can see that both of them are have a combined 3,000 peers running in non-cloud infrastructure. So it's, yeah, depends on how you look at it, relative or absolutely. Oh yeah, go ahead, Pop. Yeah, okay, cool. All right, so this was network topology. Then another area that we look into is protocol performance. And another addition to our toolset that we built this year is Herms, which is a gossip sub listener and tracer. And it was built with measurement goals specifically targeted to Ethereum again. We measure message propagation latency in gossip sub networks, number of messages received, duplicate messages in general, the bandwidth consumption as well, but this has like a little asterisk to it. And what we wanted to have as well is a lightweight deployment. So we didn't want to deploy multiple full nodes of Ethereum to the network. And our method to build a DHT host implementing all relevant protocols that are necessary to be a good citizen of the Ethereum network, and then trace all gossip sub events. And implementing these protocols means some protocols need to be forwarded to a full node, but only a subset of them. And this allows us to have very lightweight Herms instances that only a subset of protocols need to be forwarded to a full node. And this is how we can deploy multiple of these nodes without actually incurring huge infrastructure costs. And these are the events that we can trace with these Herms instances. So first of all, regular libp2p host events. Trace topics, unsubscribe events, I-haves, I-wants, so general control messages, peer scores as well, and message arrival times. But also, since Herms is implementing all the request response protocols of these Ethereum nodes, we can also track how many of these requests are made by other peers, for example, or how many we are doing to other peers. And this actually gave us quite a few nice results. I think Dave touched upon this earlier, just briefly. So first of all, we saw that we receive a lot of duplicate messages on gossip sub, which first of all gives a very a good opportunity for improvement here. And we saw that, sorry, you can see here on the right-hand side, on the x-axis, the number of duplicate messages, and on the y-axis, the is CDF of how many messages we actually have received twice, 3 times, 4 times, and so on. And yeah, for different topics in this Ethereum network. And the green line is actually corresponds to a topic which submits quite large messages, and this is also the worst line in terms of how many duplicates we receive. And yeah, so this is also the second bullet point. Bigger messages are more prone to be duplicated. And when we look at another graph here, this is the time when we receive the duplicate messages. We can see again for example, the green line here, which are blocks that are transmitted over the network, that 50% of these blocks are duplicate messages for these blocks are received within 80 milliseconds. And this time window gives room for improvement. And this room for improvement on our end was to propose the prioritization of these I don't want messages that Dave mentioned earlier. And so within these, so when we receive a message, we immediately say I don't want from any one of my mesh this message again. And this actually saves a lot of bandwidth can save a lot of bandwidth in the Ethereum network. And generally, the outcomes of this this study was that we identified gossip sub effectiveness ratios and bandwidth costs, the ratio of duplicate messages per topic, and bandwidth ratios for each gossip sub component internally, and reported some implementation difference in, for example, JVM, libp2p. It's just a different understanding of the spec, but we identified this. And we proposed the prioritization of I don't want messages because of this study. That's how we identified it. Cool, so this is Herms, and the last tool that I want to get into is Akai, which is the third pillar that we are built, like that ProBlab focuses on. So I think of, so ProBlab focuses on protocols. So we have the DHT, we have gossip sub, and now we are also looking into data availability sampling. And Akai is a generic libp2p data availability sampler with these 3 components. So we have a data source. In our case, we build it for the Avail network. So in this case, it's an Avail Lite client, which follows the head of the chain. This Avail Lite client will publish or notify the block tracker for new blocks of the network. And then the block tracker will forward this information to the daemon. And then the daemon will go ahead, save information into a database, but also continuously try to retrieve the data from the DHT or whatever, like wherever it's stored. In this case, it's the DHT. And it's generic because the block tracker could be exchanged with another component that gets the information about new blocks from another implementation, for example. And with this implementation, we are able to track, like this data here, like the timestamp of some operations, the key for the blocks or the cells that we look into, block number, rows, columns. So if you're more familiar with the DAS implementation, this would probably make more sense. And the duration of the operation, if it's actually retrievable, the number of bytes, and the error here. So this is for data availability sampling, our generic tool to measure the availability. Cool. This is already the recap. So we have, for the network topology, Nebula and ANS that we use. Then we have also tools for infrastructure and platform monitoring. So we have Boomo for Bootstrap monitoring, which was very, very valuable for the IPFS network last year. Problems are resolved now. Then Tiros, which is measuring website performance that are hosted on IPFS. For data availability, I mentioned Akai, but also we have the CID Hoarder, which is like Akai, just specialized on CIDs and IPFS. For protocol performance, we have Herms that I mentioned, but also Parsec, which measures DHT lookup performance from different geolocations. And the last one would be Ookla, which is a network bandwidth measurement tool that builds on top of Herms, but also uses data from Nebula. And this is actually what Mikael will demo in a second. But if we want to look ahead, what ProBlab is up to for the foreseeable future, we want to make this data available through an API. So we noticed that especially the network topology data is very interesting to other teams. So we were approached that people wanted to have this data for their own measurements or protocol development and so on. So we started building an API to expose this data. We obviously want to integrate additional networks. We have some specific in mind, but it's always good that we build on top of libp2p because this allows us to target multiple networks. Then one customer is interested in net traversal performance. So we did this this hole punching experiment, I think 1 or 2 years ago, and we want to revamp this potentially. And like a more general focus on the data availability sampling protocol. So these are our focus points for the foreseeable future. And with that, I would give it to Mikkel to demo one of our tools. So pray for the demo demons, and we'll see. Yeah, so Mikkel will look into, hang on, I have one slide more. Yeah, so this is Ookla. As I mentioned, so we are now at a stage where we have built like a few of tools that we can build other tools on top, which makes it much more easier to do things. And for example, Ookla is built, like uses data from Nebula, uses Herms as an implementation, which is just, can interact with the Ethereum network. And then what Ookla does is it uses the capabilities of Herms, the data from Nebula, to download carefully chosen volumes of data from peers in the Ethereum network, and then just measures the bandwidth available to them. There are some complementing methodologies to measure bandwidth. I think Shaba is here, for example, who does it differently. But this is like our way of doing it. And yeah, I would give it to you, Mikkel, if it's working.
Give me a second, I will configure the display. Doesn't seem to be working. I mean, it recognized the screen, but
what's the resolution? Go to 1280 by 720. I have like, oh yeah, it already is there. Keep changes?
No. And if you go to the back.
Try it. This table is brand new, so it should work. You're getting hacked. It's your Linux machine. Actually, Chad, do you have your USB to HDMI thing? That'll work. For some reason, we use the USB adapter. It seems to work. Oh yeah, cool. Thanks. Yeah, use that. It should work. For some reason, especially on Linux machines. Like I couldn't get mine to work when I went to give a talk the other day, but I did one of these and it worked just fine. Not seeing it. I guess we're not gonna get a demo today.
no. Well, if anyone wants to see it, yes, I'm around.
What's the demo? Why don't you guys describe what the demo is?
So
You can act it out. You know?
The idea was to make a real-time measurement of the bandwidth for nodes in Ethereum, regardless of the Wi-Fi connection. But it was pretty much like showcase like how the whole tools that are building within IFCC and PropLab are pretty much modular, so that eventually you don't have to worry again about, for example, establishing stable connections with Ethereum and having to re-implement like the communication within them. Because, for example, in this case, Herms is doing that for you. You don't have to worry about peer discovery because you can, or we can access the Nebula straight away. So you just need to focus on the specific measurement. In this case was bandwidth measurement, relying on all the underlying modules or applications. So yeah, it seems that we are not going to measure anything. But if anyone wants to have it a live demo, just come along and we'll give it a try.
Thank you, everyone. Sorry.
Yeah. So sorry, is something wrong? Okay, cool. What do you actually query the peers that you see from Nebula for, like, to measure the bandwidth? Yeah. Okay, so that's why you use Hermes.
Yeah. So the question was like, what are we actually querying from nodes in Ethereum to measure the bandwidth? So the consensus layer of Ethereum uses like libp2p protocols, and one of those protocols is you can request X number of blocks by range with a certain maximum. So the idea is that this is already implemented in Herms. Like you can already do this RPC call from the application layer. So because we are reusing Herms, what we can do is like once we know the information about nodes in the network, you can basically request like X number of blocks from them, and just like we have like custom stream readers that don't add much overhead, and the idea is that you can extrapolate the bandwidth from that measurement. Like in case you, for example, would like eventually to do like blob sampling, you should expect like a similar bandwidth for that case. Okay.
Yeah, thanks for that great presentation. Just one question in relation rather to ants. So my understanding is like if somebody's running a DHT server, they would already have that peer routing table stored. So how does ants now build on top of that? Like could you speak a little bit more about like what is actually being stored that is improving the efficiency of like nodes?
So it's not nothing about improving efficiency, or so it's more like just measuring the number of peers interacting with the network that we cannot see from the server side yet. So Nebula is like the active component, so we can reach out to peers and ask them things, and this is how we can detect all of them. Blocked by the firewall and the net or whatever. And so we need to wait for them to reach out to us. And so we carefully position these ants in the key space so that if a client joins the network, they will always contact us because of the way that the DHT works. Yeah. So now.
In regards to Herms and Ookla, are they meant to be extendable in the sense that I can add support for a different non-Ethereum network which they use libp2p?
Yes, that's the intended goal here. So Herms currently supports Ethereum, as I mentioned. One other thought that we had is extending it to Filecoin. So the biggest issue or biggest hurdle here or challenge is to implement all the different protocols that are necessary to be a good citizen in the network, so that other people or other peers don't prune you from their mesh. So Herms is in that sense like extendable. So you just need, which is a huge task. You just need to implement these protocols in a lightweight way, for example, and then all the tracing capabilities and so on would be you would get for free. So this is the idea. Yeah.
I have a few questions on Akai. First of all, is it written in Golang or Rust? Because I know Avail is in Rust. It's Go, actually. Okay, so you basically made it like a Go implementation for Avail like client.
No. I mean, the Rust DHT, it's pretty much compatible with the Go DHT. So, like, I mean, we only use the Avail Lite client to get the current view of the network. So you can rely on the Rust implementation for that. And yeah, exactly. So there is already something which is tracking the network. We just extract that information from there, and then Akai is just doing the sampling at the DHT level. But we just care about the sampling. We don't have to process anything.
Implementation of. Do you still like implement the Golang side of like the data format, right? Because the DHT is still the same protocol, but you still want to like understand what's actually stored on the DHT, right?
Yeah, in that case, the data is quite arbitrary, so it's just a number of bytes, so there is nothing like a format to follow. Yeah, it will be hard for us to actually verify the data. That will probably be like an extension or another module for that.
This is a good question. Could you just, I heard you say something too. Will you just put it on the recording? I just want to make sure it's on the YouTube video.
Okay. So the last question is the data that is DHT, that Akai gets from the DHT, is it verifiable or no? That's the question. And Michael says no, there's no verification. And currently, okay, that's also a good point. And like, what's the status of it?
So we have like a working prototype, but we're working with the Avail team. There isn't much data on the Avail network yet, so probably we will have bring updates in coming months.
More questions? Oh yeah. Go.
Test. Okay. So I will ask about two performance tools. Is it applicable for the custom libp2p networks, or is only support the protocols right now? So I will, for example, I will want to create a peer-to-peer network, and can I apply to that network your performance tools, or just only support the protocols like Ethereum, like you said?
So yes, you can apply some of these tools to just arbitrary networks, as long as they implement, for example, if your network uses a DHT peer discovery, you can apply like quite a few of these tools to your network. If your network uses Gossip Sub, for example, then you can also apply Herms, but with the caveat that I mentioned earlier, you need to implement a few things to make it compatible with yours, but you would get the tracing capabilities and everything for free here. So emotions. No. Okay, I think.
Yeah.
Oh yeah.
Test. Nope.
I'm just intrigued after he asked the question about ants. So you strategically place DST servers so that you can recognize incoming peers. But why not just use the DHT crawler to find out other nodes? Do you need that liveness information when a node is joining?
So because this is for DHT clients, we cannot reach out to them. This is what I mentioned earlier. So even though they join the DHT, they joining a DHT from their perspective is just building up their own routing table, but no one else of the network would actually get to know them. So no one can connect to them. Only they can reach out to the network. And because of that, we place previously we called them honeypots because they attract other peers to connect to them. And yeah, the way that we did it, we placed them evenly and just wait for the incoming connections. And yeah, we cannot reach out to them proactively. This is the issue here. Yeah. Okay. Shaba? Okay.
Yeah, I just wanted to ask clarification on this. You cannot reach out directly. So is this because you are calling the libp2p DHT here, or is this, or you also have this problem in DXV5 because of firewalls and NAT and everything else, like I have?
So this is a general problem for DHTs, I would say. So right now, this is only supported for libp2p-based DHTs, so we haven't implemented it for DXV5 or DXV4. But it would be exactly the same problem. No? Yeah, I will repeat it. Okay, in DXV4, you have different problems you're saying.
Yeah, so you say that that DXB5 is just like the implementation of the DHT, because in DXB5, in DXB4 you can? Okay, so okay, yeah, but from a DXB5 perspective, you always behave as a DHT server. Like at least on the libp2p side, you make a clear distinction between who actually participates in the core of the network and who just samples it. And in DXB5, my understanding is that you always behave as a DHT server, but sometimes you are not reachable. And yeah, but yeah, like in DXB5, you don't have a limit of peers that you can be connected to because you're using UDP, so you can keep 1,000 sessions open. And in libp2p, yes, but generally when you crawl it, there isn't much restriction there, at least on the libp2p DHTs. So yeah, this is pretty much like just trying to see which are the nodes or how many nodes and some metadata from them that actually don't belong to the core of the network. Like for example, if you're running a MetaMask extension on a browser, you won't be able to be as a DHT server. Or actually, if you were a DHT server, you will just disrupt in the network because you are not reachable. People will try to connect to you, and you are just disrupting the performance. So this is more like on that side, like how to actually measure how many users could actually be using the DHT. Yeah.
For a DHT like libp2p DHT, I think mostly it sees a use case in IPFS and other places. Node liveness would matter for these measurements as well, right? Because you're not able to contact probably because nodes are not live for that like for an extended period of time.
Yeah, that's totally right. Liveliness measurements are also only implemented with Nebula for the server side of things, not for the client side of things. Because as you said, we cannot reach out to them and test if they are still online. So we would. You can apply some heuristics like, okay, if they contact us within like multiple times within an hour and then within the next hour again, we could assume that they are online for the intermediate time as well. Yeah, this is how you could maybe get a metric for this. Yeah. Okay. I think we're also over time, right? Okay, cool. So one more question, or what does it mean? Just slightly? Okay. If there's one. Okay, that's good. Thank you, everyone.